let's consider a car with these two forces acting on it, as shown in this diagram, with a certain mass of 1,000 kilograms. We're saying the road is slick, so we're not worrying about friction with the wheels, and we want to know what's the net force on the car, and then what's the car's acceleration. So to get net force, we need to add together these two forces, and then to get acceleration, we'll use Newton's second law. So getting net force, we'll label them as F1 and F2. We'll use a coordinate system here, X and Y, and then we can say our net force is just the vector sum of those two forces. You can do this graphically if you prefer. Algebraically is probably going to be easier to do. So our net force, we'll get the X component first, and this will start by looking at the X component of each of those individual forces. So here, since we have the angle it makes with the Y-axis, if you think about projecting this, cosine would project this onto the Y-axis, so sine would give you the opposite side, or the X-axis. If you don't like doing this and you always want to use cosine to get your X component, you just always need the angle with the X-axis. And you can do that here by doing a complementary angle and finding that this 30-degree angle with the Y-axis for F2 ends up with a 60-degree angle with the X-axis, and then always use cosine. Here I'm going to show you using sine here, where we say F1 has an angle of 10 degrees with the Y-axis, so the opposite side is the X, so this should be a negative because it's going to the left, and it will be negative the magnitude times the sine of 10 degrees. So that'll be negative 380 newtons times the sine of 10 degrees. And then for the F2, it will be the magnitude 450 times the sine of 30 degrees. I encourage you, if you got lost by that, to draw out the right triangle and verify that this works out for you. Plugging those in, we get 159 newtons. So we have the X component of our resultant. We now do the same thing for the Y. We get these components, which are both going to be positive because they're both acting upward. And this will now be cosine of 10 to project this onto this axis. It's the adjacent side here, so cosine will give us the value we're looking for. And for F2, it will be cosine of 30. So we get 380 newtons times cosine of 10 degrees plus 450 newtons times the cosine of 30 degrees. And that should sum to 764 newtons. Our overall net force then is going to be the X component in the I hat direction plus the Y component in the J hat direction, or 159 I hat plus 764 J hat with units of newtons. If you wanted magnitude and direction, you could do that, but if you're just asked for net force, this is a perfectly valid way of expressing a net force in component form. For part B, we want to know what's the acceleration. So we'll use Newton's second law and say that my net force is equal to mass times acceleration. I want to solve for acceleration, so I divide both sides by mass, and I get acceleration is equal to force over mass. I'll just write this in vector form. We could have split this up and considered the X component and the Y component separately and then recombine them. Here, because it's simple enough, I'm just going to write the vector expression with the I hats and the J hats divided by my scalar 1,000 kilograms. And when I divide that, the newtons, which is kilogram meters per second squared, the kilograms cancel and we're left with meters per second squared as our units, with an acceleration, as shown here, 0.159 in the I hat plus 0.764 in the J hat, with units of meters per second squared.